In this representation, we introduce our work, self-involved dynamic expansion model for task-free continual learning. Continual learning is an important topic in computer vision. It aims to learn a model that can continually capture the new knowledge without forgetting all previously learned information. However, the main problem for continual learning is network forgetting, which can significantly decrease the model performance when learning a new task. However, most existing models are only focused on general continual learning, where the task information is always given during the training. In this study, we address a challenging task called task-free continual learning, which assumes that the model cannot access any task information during the training. However, the main difference between general continual learning and task-free continual learning is that task-free continual learning enables the model to be trained on the streaming data without receiving any task labels. There have two major problems for the task-free continual learning. First problem is the network forgetting. The second problem is that the existing dynamic expansion model usually creates a large model structure during the training. So in order to address those two problems, firstly, we address the network forgetting by introducing a new dynamic expansion model. Secondly, we want to learn a compact model structure by introducing a new self-assignment mechanism. Specifically, we compare the distance in the output between the current expert and other remaining expert. If such a distance measure is large, it demonstrates that the current expert has learned no enough information, and we should preserve the current expert and build the new expert. The proposed dynamic expansion model can ensure a compact model structure where promoting knowledge diversity among experts. The overall learning procedure of the proposed method can be divided into the three steps: the sample selection, the training step, and also the checking model expansion. In the first step, sample selection, at a certain training step, we firstly calculate the selection score for each incoming sample by using the following equation, where C is the total number of classes, X and Y is a certain data sample. By using this equation, we can select the important sample into the memory buffer. In the second step, the training step, after the sample selection, we update the current component on the memory buffer by using the two loss functions. The first loss function is used to update the classifier. The second loss function is used to update the variation autoencoder. In the third step, check the model expansion. We assume that the model has a k expert at a certain time. We check the model by using the following equation, where we have this hold which can control the model expansion process. Specifically, we compare the similarity measure between the current expert and the other expert as the expansion score. If such a similarity measure is very large, we will build the new expert. This approach can enable us to build the diverse expert during training. In the experimental results, we firstly perform the classification task on the three datasets. This table shows that our method outperforms all baseline on the three datasets. In addition, we investigate the model performance when changing this hold. We can find that the larger this hold can lead to more components during the training. We are also improving model performance. In conclusion, in this paper, we propose a novel model for task-free continual learning, which evaluates the diversity score among experts as the expansion signals, ensuring a compact model structure. Secondly, we introduce a new sample selection approach which can further improve